Hi class, in this video here what we want to discuss is exponential growth and decay, and specifically what we want to talk about is exponential growth and decay models. All right, and what we're going to do is we're going to work a bunch of application problems here today. And I personally think the problems are fun. And as we're going to work through them, after I introduce the formula for exponential growth and decay, we're going to do, as I said, these problems. You're going to need your graphing calculator. So have that, or any scientific calculator, have that handy as we work through this. Okay, so the first thing we're going to do is we're going to talk about how you model exponential growth and decay. And then what I'm going to do is I'm going to do a quick example of something called logistic growth models. All right. So what exactly is an exponential growth and decay model? What does it look like? Okay, so the mathematical model for exponential growth or decay is given by the following. So f of t, if you want to write it in function notation, is equal to a sub 0 times e, and then e is raised to the k times t power. Or another way of saying it is a, the amount, is equal to a sub 0 times e to the kt. Okay, first off things. There's three parts to this equation that you're going to need. You're going to need to figure out what a sub 0 is, k, and what t is. Okay. Now here's the thing. If this value, first off, if k is greater than 0, the function models the amount or size of a growing entity. And if k is less than 0, okay, so this k value is really important, okay? If k is less than 0, the function models the amount or size of a decaying entity. All right, in each case, a sub 0 is the original amount, okay? So a sub 0 is the original amount you have. Or the original amount or size, okay? And if it's k is greater than 0, it's a growing entity. And if k is less than 0, it's a decaying entity. And this is at t is equal to 0. And a then, this value a, is the amount you have at time t. So t is some variable for time. And time can be measured in years, in seconds, in minutes. It just depends on the problem. And here, and k is a constant representing the growth rate. So k is the growth rate. All right, so what it's going to be our job to do, okay, is when we do these problems, we have to figure out, the values of a sub 0 and k here. T is going to be the variable we're going to plug into this, okay, because you can see in function it's f of t here. All right, so keep these formulas handy, okay. All right, in exponential growth here, this is when k is greater than 0. You can see that the value is growing, increasing, increasing, increasing. And when k is less than 0, it's negative. You can see the values decreasing, going down like this. All right. Let's work some examples here. All right, I'll do one of exponential growth, and then I'll do an example of exponential decay. All right, so here's an example of growth first. And this is about the population of Israel. So in the year 2000, the population of Israel was approximately 6.04 million people, okay? So in the year 2000, the population here, 6.04 million. And by 2050, it is projected to grow to 10 million. Okay, so 50 years later, the population here now is projected to be 10 million. Sorry, 50 years later, it's projected to be 10 million people. The problem says use the exponential growth model. A is equal to a sub 0 e raised to the kt power, in which t is the number of years after 2000, to find an exponential growth function that models the data. Okay, we'll do that. And then the next question says, in which year will Israel's population be 9 million? Okay. Let's do this. So part A. part A says we need to find this model. A is equal to A sub 0 e to the kt. Well, look, you need these things. First off, you need A sub 0, and that's the starting amount. And if you look here, well, we're starting at the model at years since 2000. Okay. Well, do we know what Israel's population was in 2000? Yes. Yes, it was 6.04 million people. We know T is going to be years after 2000. Okay. What we need to find then, we need to use some tricky math here to find K, the growth rate. All right, so how are we going to do that? So the amount A is equal to, I'm going to plug in what I know, 6.04 e to the kt. Oh, shoot, how are we going to do this? Well, going back, look, I know 50 years later, the population is supposed to be 10 million people. So look, when T is equal to 50, the amount should be 10 million people. Now look, now I just need to solve this, okay? So how am I going to do that? First off, I need to get the E by itself, okay, if I want to solve for K. So I'm going to divide the 6.04 over. Well, then how are you going to get K by itself? You're going to take the natural log of each side. Well, natural log of E raised to the K50 power, so this is just K times 50 is equal to the natural log of 10 divided by 6.04. And then look, how are you going to get K by itself? Now just divide by 50. You're going to need to grab your calculator at this point. Just be very careful in your calculator here. Be meticulous, okay? So you're going to need to take the natural log of 10 divided by 6.04 and then divide that by 50. Look, you're going to have to go out pretty far here. I'm going to go out 5 decimal places. So 0.01008. Okay, so 0.01008. So what that means, that the model, as we can say, the population, A, is equal to 6.04 times E, my growth rate, is 0.01008 times T. And T is years after 2000. Okay, so part B then is asking when, so it's saying when will the population be 9 million? So it's asking you to solve for T here. So when will population be 9 million? Well, so I'm just going to plug 9 in for A here. So it's 9 is equal to 6.04 e to the 0.01008t. Now again, you're just going to follow the same process and solve for t here. Okay, so divide the 6.04 over. Take the natural log of each side. So then you're just left with natural log e here. You're just left with 0.01008 times t is equal to the natural log of 9 divided by 6.04. And so you can just see when you divide this over, t, the year, will be the natural log of 9 divided by 6.04, all divided by 0.01008. And let's see what year that is. So it's natural log of 9 divided by 6.04. Okay, and then you're going to divide that by 0.01008. And you get roughly 39 point, I'm going to say, I'm just going to actually round this to 40 because we're looking years. So it's going to be roughly 40. So you got to remember that's years since 2000. So our model predicts that in 2040, the population will be 9 million. All right, because remember, this is years after 2000. All right. So that's an example of exponential growth. All right. Now let's do a fun one with exponential decay here. All right, so the half-life. Okay, so the half-life, what that means is it's how long it takes for half of a substance to be left. So if you have 1 gram of it, if the half-life is 10 hours, okay, that means you have 0.5 grams left in 10 hours. And then 10 hours after that, you have 0.25. And then 10 hours after that, you have 0.125, and so on. It keeps cutting in half. All right, so it turns out the half-life of aspirin in your bloodstream is 12 hours, okay? How long will it take for the aspirin to decay to 70% of the original dosage? Okay. First thing we need to do here to solve. We need to find the decay model because the amount is decaying. All right. So it's the amount is equal to A sub 0 E to the KT. This is what's interesting. Do you notice that this problem doesn't even tell you how much you took? Okay. So let's just say, okay, it doesn't tell me how much I took. So let's just say I took 1 unit, okay, 1 gram, 1 ounce, whatever, how much ever you're taking, 1 milligram, okay? Like that. So I now have to figure out, to be able to ultimately solve this, I need to figure out what K is again. I need to figure out what the decay rate is. Well, I know after 12 hours, there will be half of it left. So the amount when T is 12, all right, if I let T be hours after taking, there will be 1/2 of it left. Well, look, you just have to solve this, okay? The 1 doesn't matter, so you have e to the k times 12 equals 0.5. Let's take the natural log of each side. Well, again, you can see exactly what's going on here. So you have k times 12 is equal to the natural log of 0.5. All right, so K, the decay rate, got to figure out what natural log of 0.5 divided by 12 is. And it absolutely makes sense that this is a negative number, right? Because it's decay, so K has to be less than 0. So negative 0.05776. I'll go out again, 5 decimal points here. Okay, so this is what I got. The amount in the bloodstream, okay, is equal to 1 times E to the negative 0.05776. And this is for every one unit that you take, or one dosage, okay? So if I want to figure out how long it will take for the aspirin decay to 70% of the original amount, well, that would be, I'd have 0.7 dose of a dosage left. So plug in 0.70 for A, and it's asking you how long, and so solve for T. So 0.70 is equal to, I can drop the 1, E to the minus 0.05776 T. Take the natural log of each side. Well, again, you're left with negative 0.05776 T is equal to the natural log of 0.70. And look, T is equal to, just dividing this over, the natural log of 0.70 divided by negative 0.05776. Let's figure it out. So look, if you take the natural log of 0.70, you're going to get this a negative number. That's why you have to make sure you got your signs right here. So divided by negative 0.05776. I'm going to round this to 6.2. So it's going to be roughly in 6.2 hours, okay? You're only going to have 70% of the original dosage in your system. Okay. Let's now talk about logistic growth models. Okay. So the mathematical model for limited logistic growth is given by this. Okay, f of t is equal to c divided by 1 plus a e raised to the negative bt. Or the amount A is equal to C divided by 1 plus A times E raised to the negative BT. And this is what the graph of this looks like, okay? You have initial like increasing growth rate, and then eventually the growth rate decreases and it levels off at this, at some value, okay? It's gonna, like it hits limits, it hits a horizontal asymptote, okay? So there's limited growth. And so the reason this is like, so from population growth to the spread of an epidemic, nothing on Earth can grow exponentially indefinitely. Okay, like this is where there's some limiting amount, like it stops. It can only grow so much. So the logistic growth model is a function used to model situations just of this type, okay? And in this problem here, what I want to do is I'm going to give you the model. I'm not going to ask you to solve for anything. I'm going to tell you what the model is, and we're going to go from there. All right, so this one here, okay, the logistic growth function, f of t is equal to 100,000 divided by 1 plus 5,000 times e to the negative t, okay? Just describes the number of people, f of t, who have become ill with influenza t weeks after its initial outbreak in a particular community. Okay, so here's the first question. A, how many people became ill when the epidemic began? Well, that's t weeks after the initial outbreak, so this is just asking you to find f of 0. So it's literally asking you to plug 0 into this. So you can take 100,000, divide it by 1 plus 5,000 times e. If I plug 0 in for t, you get 0. Well, e to the 0 is just 1, right? Because anything raised to the 0 is 1. So this is literally, you're just going to take 100,000 and divide it by 5,001. So we're going to round this off, okay? Because you can't have 0.99 of a people. So what we're saying is look, when this outbreak initially started, roughly 20 people, okay, had this influenza. All right, so how many people were ill by the end of the 4th week? So remember, T is number of weeks. So F of 4 would tell me how many. So it would be 100,000 divided by 1 plus 5,000 e to the negative 4. All right, got to be careful with your calculator here. It's going to take 100,000. You're going to divide it by, and then in parentheses, 1 plus 5,000 times e to the negative 4. And looks by the end of the 4th weeks, it's roughly 1,080 people. Okay. At this point, I'm going to round this down. So it's roughly 1,080 people. And so what's really great about these models, it says, okay, what is the limiting size of the population that can become ill? And the limiting size, all right, for all these models is the value, if you look back in the in our model here, it's the limiting value C, whatever the numerator is. So in this case, it's 100,000 people. And look, let's just plug this in our graphic calculator, and just so you can see what this looks like. Okay. So we're going to go 100,000 divided by, now in parentheses, 1 plus, just a little mistake there, 100,000 divided by 1 plus 5,000 times e raised to the negative t. Well, what's really tough here is this graphic calculator. You can see it just, it looks like it shoots up really, really quickly. And then you'll notice here, all right, and this is where it gets a little confusing. You'll notice on mine, like the blue stops somewhere. That's because the graph literally whoosh, goes up and then just stops there. Okay, it hits that horizontal asymptote. So the graphic calculator kind of does like a bad job there, but you can at least see where it's stopping right there. Okay, so I hope this lecture helped talking about exponential growth and decay, and then a quick introduction to this logistic growth.